Good morning, viewer. Welcome to our first activity. Here's the breaking news. Yes, long-lived fungi are the latest organisms to go under the microscope in search of new understanding as to why they don't occur life-limiting mutations given their age. Researchers at Wageningen University in Netherlands set out to compute the peculiarities of multicellular growth in filamentous fungi. What they ended up with was a new hypothesis explaining how certain types of fungi keep a lead on freeloading mutation that accumulate in their thread-like mycelia, the root-like structure of fungal colonies. The filaments of mushroom-forming fungi spend much of their long lives with two separate nuclei, each containing one half of a full set of chromosomes. Only in the gills of mushrooms, moments before forming spores, to the two haploid nuclei mesh together in a brief union to reproduce asexually. Mutation in other nucleus rob the affected mycelium of its ability to fuse its spindly filament to another, forcing other mycelia to pay the cost in spore formation. Given enough time, mutated mycelia will dominate the fungus, reducing its ability to make spores at all. First discovered in last growing Neurospora crassa mold in 2016, the mutated nuclei are duff cheaters for the way mutated mycelia cannot begin asexual fusion with their own filaments to form spores, but can piggyback off other fully functioning mycelia they may encounter. These biological tensions between individual cells and whole organisms echoes considered in other organisms where mutant cells hellbent on replicating grow so fast they harm the animal in which they arose, sometimes fatally. Because these fungal mutations are selected within the mycelium but reduce the fitness of the mycelium as a whole, you can think of them as a kind of nucleus cancers, explains evolutionary biologist and lead author Duar Anand of Wageningen University. Anand and colleagues compared fast-growing molds and long-lived mushroom mycelia that can live for hundreds of years. They suggest the latter use a special type of cell division called a clamp connection to screen against selfish mutants, enabling them to live long lives without answering too many genetic faults. In this form of cell division, one of the filaments haploid nuclei is interned in a holding bay until the cell can check its quality and the filaments fusion is possible. Both nuclei are continuously testing each other for the ability to fuse. A test that nuclei with mutation in fusion genes fail, explained Anand. If the cell cannot fuse, it means a dead end for the cell and thus the end of its nucleus. In humans and other animals, cancer develops after an organism accumulates enough genetic errors to unleash runaway cell division, seeing those errors pile up over time. You would think that creatures with long lifespans or large bodies would develop more tumors, but elephants and whales defy that reasoning, deploying molecular tricks to repair damaged DNA, keep cell division in check and suppress cancer. These evolutionary solutions to Peto's paradox, as it's known, are of great interest to scientists or anyone who had liked to prevent cancer. Beyond the report, for activity.